So in this lecture, we're going to look at the set ADT with bit vectors. So again, this was just one of two implementations we looked at. The previous one was looking at arrays, but now we're going to look at the implementation using bit vectors. Let's look at bit vectors. So firstly, we're going to let items be positive integers. For example, 1, 2, 3, etc. We could look at positive numbers. We could handle negative integers as well, although we'd need to do some arithmetic to do that. We're going to represent our set using a vector of bits. So item I belongs to set if the vector has value 1 in the position I minus 1. Otherwise, the item is not in the set. So let's look at our example here with our vector of bits, and we can use that using a binary representation of an integer. So if we look at value 1, so therefore we do 1 minus 1, which is bit 0, and because it's 0, it's not in the set. If we look at bit 1, which is basically looking at 2, the value 2 is in the set because its value is 1. Then if we look at the value 3, it's not in the set because 3 minus 1, which is bit 2, is equal to 0. So therefore, based on that information, we can say the vector represents set with a single item being 2 in it. So how do we handle bit vectors? So again, how we're going to handle all the different operations that we want to do on sets. We're going to use bitwise operations on integers to do that, remembering that we're using an integer to represent our overall bit vector. So we're going to use bitwise OR and negation, and also logicals shift left and right to apply each of the integer operations. So let's look at an example. Now that we can see bits 0 and 1 have been set in this example, so that means this set or this integer is going to actually represent the set containing the elements 1 and 2. So we'll call that S1. And in this second one, we can see bits 1 and 2 have been set to 1. So therefore, that's going to contain the elements 2 and 3. And if we have this resulting set, if we apply our union operation, we can see the combination is going to be 1, 2, and 3 are the elements that are going to be in the resulting set of applying the union operation. And in this example, if we wanted to do the intersection, we can use bitwise AND to basically see when we've got both bits equal to 1, then we know the resulting bit will be equal to 1 as well. Okay, so possible bit vector implementations of a set. So we create a new set, and for example's sake, we're just going to put a capacity of 32 on this integer, so it can only have 32 bits. Now, in reality, Python doesn't have it has an arbitrary bit length, but for argument's sake, we're just going to assume our integers or our integer representation is just limited to 32 bits. So we initially set our elements or our integer equal to 0. So that's going to basically mean all the bits are also going to be therefore equal to 0. We're going to add item 3 to our set. So all we need to do, like we saw before, is it's going to set bit 2 equal to 1. And if we add item 31, then all we need to do is add bit 30 equal to 1 as well. How about removing an item? Well, in that case, all we need to do is make sure the element is then set, or the bit is set to 0. So in this example, we're removing item 3, so therefore we just then go and set bit 2 equal to 0. Pretty straightforward. In both cases, it's okay because we're just setting the operation, so whether it's adding or removing, it's fine because we just make sure that bit is there, and we can't obviously have duplicates, so that's fine. We can't have a duplicate bit. So we've applied all the requirements that we need to do for sets that we don't have duplicates, and in this example it's unordered. We don't know. We don't have a specific order. Okay, how do we set bits 1 to 0 in an integer? Basically on what we wanted to do, just in adding or removing elements. So assume we have an integer I where some bits are 1 and some are 0. So in this example, we want to set bit I equal to 1. You can see it's currently equal to 0. So we create another integer b with all the bits set to 0 except for the bits that we're trying to set. So in this example, only the ith bit is set to 1. So we're going to create that bitwise representation using an integer, and the way that we can basically create that integer is by shifting 1 all the way left to the ith bit. So that will create that pretty much bit mask, we may call it. And then we're going to apply a bitwise operation, A or B, so that way it's going to be true if at least one of them is true. So that means we're going to get all the elements in set A, our original integer. Also, it's going to make sure that it adds the new element as well, or that new bit which is in the ith position. So the result should be that we get the original set plus the ith element set to 1. So let's have a think about how we can set the ith bit to 0. Now, we're not going to give you perhaps a solution for this, but maybe consider how you could use a bit mask and then apply maybe an AND operation to try and set that particular bit to 0. So let's actually look at the implementation now. If we remember, we had our abstract set from before, so we're going to implement that again. We're going to, obviously that will be the parent class. Similar to what we've seen before, we've got a dummy capacity or minimum capacity. Now remember that it's maybe not as needed because integer could be of arbitrary size, but now in our example we're probably going to consider just 32 for our maximum size. Like before, we're going to have clear, so all clear does is set all bits to 0, and the way we do that is we set our integer, which is called elements, to 0. Length becomes a bit trickier. Remember, with the array implementation, it was pretty straightforward. We kept track of the size, but as we'll see, that it's not so easy to see the number of bits that have been set to 1 in our bit vector. Checking if it's empty is pretty straightforward. We just see if the integer or all bits have been set to 0. That would tell us if it's empty or not. And indeed, that's our initial state. We have an empty set to begin with. And for is full, we just return false because we're dealing with arbitrary length here. In reality, we could add any integers to our set and have any possible size for our overall elements, which is our integer. Big O complexity, all return statements, assignments, and integer comparisons, we're going to assume it can be done in constant time. The set in it calls clear, but we also know clear is O1, so that's pretty straightforward. And therefore, everything here, except for length, is going to be O1. Like we said, because it's trickier, we'll look at the complexity of that a little bit later. So implementing the contains. This implement method implements the member operation. So we can handle integer items only. So we're going to see if this bit is being basically set to 1 or not. And the way we do that is we shift this bit all the way to the right and then AND it with 1 to say that if both of them 1, then obviously this bit itself would also be 1. So that's how we do it, basically of what I just said, to shift it over and AND it with 1 to see if this current bit item is contained in our set. So what's the worst case complexity? Well, all items, return statements, arithmetic, and bitwise operations are O1. Therefore, the overall complexity is also O1. So let's implement the add operation. So all we need to do in this case is set the correct bit to 1 and then apply an OR based on that mask. So we're going to take our current set and then OR it with the correct bit, which is item, so therefore we can then add that item to our set. So to do that, all we're going to do is get 1 and move it all the way to its kth position, which is based on item, or the item's position. And therefore, if we move that, that's like a bit mask. We're then going to OR that to say that take the original number and then OR it with this mask to therefore add it to our set. Again, if it's already set to 1, then that's fine as well, because it will just ignore it. If you've already set the bit, setting it to 1 again will do nothing, which is great because, again, we don't want to have duplicates in our set. So we can handle integer items only. So that's basically the limitation of what items that we can add to our set. Again, there's 2 bitwise operations left and the bitwise OR operation, which we said, and because for the big O complexity we've got no return statement and everything else is an arithmetic operation, the overall big O complexity is O1. So you're going to try and implement the remove on your own, and like I said, a bit of a clue for that was you may want to use a different bit mask. You may want to try and basically do the complement or the of the bit mask we're currently using. All ones except the current item should be set to 0, and perhaps you could do something like an AND operation to get the resulting elements. Let's look at union. Recall that a union of self and other is what we're trying to aim for here. So we create our resulting set, and to do the union between the current elements and our other elements, all we need to do is apply the union operation on those 2 integers. So all we need to do that is our OR operation between the 2 integer representations of our bit vector. Then overall we just return the result. So it's quite simple. It's because all we need to do is basically combine them together to combine the bits together to get the overall representation of all the elements that are in our set. What is the worst case complexity? Once again, everything is O1 for the same reason we've said before. And therefore it is O1 overall. Great. So you can try and implement difference and intersection on your own, and you can look back at those operations to see some clues on how you may want to do that. So the problem is surprisingly length. If we remember from before, length was quick with the array implementation. It was some of the other operations that were slow. But because in this implementation, what we've seen so far, all the operations have been pretty much O1 so far. Let's have a look at why we can't keep track of the length, and it's to do with the fact that we've used cheap bitwise operators to do the adding and removing. It's been hard to keep track of the actual length as we've gone along, so there's no variable to keep track of that. Therefore, we actually have to count. So for example, when we're adding or removing, because we just did these operations, we didn't actually know whether we added the item or the item was already there. Similarly, when removing, we don't know if when we removed it was removed or not. So therefore, we can't keep track of the number of elements. So therefore, we're going to have to go through and count. So based on our element, which is our integer, we're going to go through each of the bits and see how many have been set to 1, because that will tell us how many elements we have in our set. So we're going to initially assume that the size is 0. And we're going to go through each of the bits. Like I said, there's a function that we can use based on an integer. We can see how many bits is used to represent that particular integer, because that will tell us how many bits we need to go through to see if each of the number or items are in the set or not. So starting from 1 up until the nth bit in our number. So this is an example of how the function works. So for example, if we had a binary representation of 37, you can see that we've got 6 bits. So if we actually run this function on 37, our integer, we see what is the number of bits used to represent that. We can see it's 6. So therefore, in this particular example, we just need to check from numbers 1 to 6 to see if they're in our set, 1 to 6, and we do that by examining bits 0 to 5. So if the item is contained in this, so that means that the current bit or the item that I'm looking at has been set to 1, which again was pretty straightforward. We just shifted all the way to the right and see if it's AND with 1 to see if it was actually equal to 1. So if this item is inside our bit vector, we know that it is part of our set, so therefore we increment 1. And then after we've done that for each of the items, we just return the size. So that's pretty straightforward. We'll just go through and count each one. So each operation performs O1 operations, and as a result, the big O complexity is actually dependent on the number of bits, or the overall size of the number of elements. Now, if we're looking at size, we're really looking at how many the bit representation, right? In our example, we had 6. So if we look at that in a bit more detail, what does the overall size of elements means? It's not the ON in this example. It's not the number of elements in our set. It's not the number of bits that we've set to 1, but it's more dependent on the overall bits that are used to represent our number. So if we have a look at an example, if we had 1 million, we've only got a single element of 1 million, and in this example we'd have to iterate through all these bits, 1 million bits, to basically see that bit 99999, which is the number 1 million, is actually in our set. So even though, again, that our size is still 1, it's still going to take that many iterations to actually work that out. So just be careful, again, how you define your big O complexity. It's not what we define the size or the input size to be. In this case, like we said, it's the input size is based on the number of bits in our integer representation of our bit vector. That is it for this lecture. We'll see you in the next lecture and just basically summarize it all to look at the pros and cons of this particular implementation.